In the beginning, there was nothing but the vast, infinite darkness of space. No stars, no planets, no light, just an endless void stretching beyond imagination. But within this emptiness, something extraordinary was about to unfold. A story that would span billions of years. A tale of cosmic violence, patient transformation, and ultimately, the birth of the only world we know that harbors life. 4.5 billion years ago, in a spiral arm of what would one day be called the Milky Way galaxy, a massive cloud of gas and dust drifted silently through space. This wasn't just any cloud. It was a stellar nursery, a nebula pregnant with the potential for countless worlds. The cloud was enormous, stretching across light years, and within its swirling depths lay the raw materials that would become our solar system. For millions of years, this cloud remained relatively stable, rotating slowly in the cosmic dance of gravity and momentum. But then, something changed. Perhaps it was the shock wave from a nearby supernova, or maybe the gravitational influence of a passing star. Whatever the cause, the delicate balance was disturbed, and the cloud began to collapse in on itself. As the cloud contracted, it started to spin faster, like a figure skater pulling in their arms. The center grew denser and hotter, while the outer regions flattened into a rotating disk. At the heart of this cosmic whirlpool, temperatures and pressures soared to unimaginable levels. Nuclear fusion ignited, and our sun was born in a brilliant flash of light that pierced the darkness for the first time in this corner of the galaxy. But the sun's birth was just the beginning. Around it, in the swirling disk of leftover material, something remarkable was happening. Tiny particles of dust and ice began to stick together, drawn by the weak but persistent force of gravity. These microscopic collisions created slightly larger particles which in turn attracted more material. It was a slow process, taking millions of years, but gradually these cosmic snowballs grew larger and larger. In the inner regions of the solar system, where temperatures were scorching hot from the young sun's fierce radiation, only rocky materials could survive. Metals and silicates condensed from the stellar winds, forming the building blocks of what would become the terrestrial planets. Further out, where it was cold enough for ice to form, a different kind of world was taking shape. Among the countless planetesimals, as these early building blocks are called, one was destined for greatness. It was located in what scientists now call the habitable zone, that perfect distance from the sun, where temperatures would allow liquid water to exist. This wasn't yet Earth as we know it, but rather a proto-Earth, a molten ball of rock and metal that was constantly being bombarded by asteroids and comets. The early solar system was a violent place. Collisions were frequent and catastrophic. Each impact added more mass to the growing planets, but also generated tremendous heat. The proto-Earth was essentially a ball of molten lava, its surface temperature reaching thousands of degrees. The atmosphere, if it could be called that, was a toxic mix of hydrogen, helium, and various other gases, nothing like the life-sustaining envelope that would develop later. Then came one of the most significant events in Earth's history, the giant impact, about 4.5 billion years ago. A Mars-sized object, which scientists have named Thesia, collided with the proto-Earth. This wasn't just any collision. It was a cosmic catastrophe of unimaginable proportions. The impact was so violent that it nearly destroyed both objects, sending massive amounts of debris into orbit around Earth. The energy released from this collision was so enormous that it vaporized both the impactor and a significant portion of Earth's mantle. The planet's surface became an ocean of molten rock, glowing red-hot against the darkness of space. But from this destruction came creation. The debris from the impact gradually coalesced to form our moon, forever changing Earth's destiny. The moon's formation had profound consequences for our planet. Its gravitational pull created tides that would later play a crucial role in the evolution of life. It also stabilized Earth's rotation, preventing wild climate swings that would have made life extremely difficult to establish and maintain. As the bombardment gradually decreased, the Earth began to cool. Water vapor in the atmosphere condensed and fell as rain, not just any rain, but a deluge that lasted millions of years. This was the beginning of Earth's oceans, though they were nothing like the blue waters we know today. They were hot, acidic, and filled with dissolved minerals from the constantly changing crust. The young Earth was still a hellish place. Volcanic activity was intense and constant. The atmosphere was thick with carbon dioxide, methane, and other gases that would be toxic to most life forms today. There was no oxygen to breathe, no ozone layer to protect against deadly ultraviolet radiation from the sun. The surface was constantly being reshaped by lava flows, earthquakes, and continuing impacts from space debris. But even in this seemingly inhospitable environment, the conditions for life were slowly being established. The oceans provided a stable environment where complex chemical reactions could take place. Deep underwater, near volcanic vents, hot springs created unique conditions where organic molecules could form and interact in ways that weren't possible on the chaotic surface. For hundreds of millions of years, Earth remained in this primitive state. The planet was gradually cooling. The bombardment from space was decreasing, and the crust was beginning to solidify into the first stable landmasses. These weren't continents, as we know them, but rather scattered islands of solid rock floating on an ocean of molten magma. Around 4 billion years ago, something extraordinary happened. In the depths of Earth's oceans, the first life forms appeared. These weren't anything like the plants and animals we see today. They were incredibly simple, single-celled organisms called prokaryotes. They had no cell nucleus, no complex internal structures, just the basic machinery needed to survive and reproduce. These first life forms were anaerobic, meaning they didn't need oxygen to survive. In fact, oxygen would have been toxic to them. They fed on the chemical energy available in their environment, processing sulfur, iron, and other elements in ways that seem almost magical to us today. They were essentially living chemistry sets, converting raw materials into energy and creating waste products that would gradually change the composition of the oceans and atmosphere. For the next billion years, these simple organisms were Earth's only inhabitants. They lived in the oceans, in hot springs, in any place where liquid water existed, and conditions allowed for their basic chemical processes to continue. They were incredibly resilient, surviving temperature extremes, radiation, and chemical conditions that would instantly kill any modern life form. But these tiny pioneers were doing more than just surviving. They were preparing the stage for everything that would follow. Some of them developed the ability to harness energy from sunlight through a process called photosynthesis. This was a revolutionary development that would fundamentally alter Earth's destiny. The early photosynthetic organisms called cyanobacteria began converting carbon dioxide and water into organic compounds, releasing oxygen as a waste product. At first, this oxygen was quickly absorbed by iron in the oceans, creating rusty red deposits that we can still see in rock formations today. But gradually, the oxygen began to accumulate in the atmosphere. This period, known as the Great Oxidation event, was actually a catastrophe for most existing life forms. Oxygen was toxic to the anaerobic organisms that had dominated Earth for over 1 billion years. It was the first Great Extinction event, wiping out countless species that couldn't adapt to the changing conditions. But for the organisms that could survive in the new oxygen-rich environment, it opened up incredible possibilities. Oxygen is a much more efficient source of energy than the chemical processes that early life had relied on. Organisms that could use oxygen could grow larger, move faster, and develop more complex behaviors. Around 2 billion years ago, another crucial development occurred: the evolution of eukaryotic cells. Unlike their prokaryotic predecessors, these cells had a nucleus and other specialized internal structures called organelles. This might seem like a small change, but it was revolutionary. It allowed for much more complex cellular processes and paved the way for multicellular life. The evolution of eukaryotic cells also marked the beginning of sexual reproduction. Instead of simply copying themselves like bacteria do, organisms began exchanging genetic material with each other. This dramatically accelerated evolution, creating new combinations of genes and allowing life to adapt more quickly to changing conditions. For the next billion years, Earth remained a world of single-celled organisms. The planet looked completely different from today. The continents were smaller and arranged differently due to the constant movement of tectonic plates. The atmosphere was still very different, with much higher levels of carbon dioxide and lower levels of oxygen than today. The climate was generally warmer, with no ice caps at the poles. Around 1 billion years ago, the first multicellular organisms appeared. These weren't complex creatures. They were more like simple colonies of cells working together, but they represented another crucial step in the evolution of life. For the first time, different cells could specialize in different functions, leading to more efficient and capable organisms. The late Precambrian period, around 600 million years ago, saw the emergence of the first complex multicellular life forms, known as the Ediacaran biota. These were strange, soft-bodied creatures unlike anything alive today. They lived on the ocean floor, filtering nutrients from the water or absorbing them directly through their skin. Some looked like ferns, others like quilted discs or bizarre fractal patterns. These creatures lived in a world that was still very different from ours. The oceans were relatively shallow. The climate was generally mild, and there were no predators. It was a peaceful time in Earth's history, but it wouldn't last. Around 540 million years ago, life on Earth exploded in what scientists call the Cambrian Explosion. In a relatively short period of geological time, complex organisms with hard shells, eyes, and sophisticated behaviors appeared in the fossil record. This wasn't just gradual evolution. It was rapid diversification on a scale that has never been repeated. The Cambrian seas were filled with creatures that seemed like they came from an alien world. Trilobites scuttled across the sea floor on dozens of legs, their compound eyes scanning for food and danger. Anomalocaris, a meter-long predator with grasping arms and a circular mouth full of teeth, was the apex predator of its time. Hallucigenia walked on 7 pairs of spiny legs while defensive spines protected its back. This explosion of life coincided with another major change in Earth's environment. The atmosphere had finally reached modern oxygen levels, allowing for larger, more active organisms. The development of hard shells and exoskeletons provided protection from predators and support for larger bodies. For the next several 100 million years, life remained confined to the oceans. The land was still a harsh, barren environment, with no soil, no protection from ultraviolet radiation, and wild temperature swings. But gradually conditions began to change. The ozone layer, formed by oxygen in the upper atmosphere, began to shield the surface from deadly UV radiation. Simple organisms like algae and bacteria began colonizing the edges of land, creating the first primitive soils. Plants evolved from aquatic algae, developing the ability to survive out of water by creating waxy coatings to prevent water loss and root systems to absorb water from the ground. Around 450 million years ago, the first simple plants appeared on land. These were small moss-like organisms that stayed close to water sources, but they were pioneers, beginning the long process of transforming the land into a habitable environment. Their roots broke down rocks, creating soil. Their bodies provided food and shelter for the first land animals. The colonization of land was a gradual process that took millions of years. Plants evolved larger size, more complex root systems, and eventually developed wood, allowing them to grow into trees. The first forests appeared, creating entirely new environments and habitats. Animals followed plants onto land. The first were simple arthropods like millipedes and primitive insects, feeding on decaying plant material and each other. Gradually, more complex animals evolved, including the first vertebrates to leave the water. Around 365 million years ago, the first amphibians evolved from fish. These creatures could survive both in water and on land, though they still needed to return to water to reproduce. They were the ancestors of all land vertebrates, including eventually reptiles, birds, mammals, and humans. The late Paleozoic era saw the formation of the supercontinent Pangaea, as Earth's tectonic plates moved and collided. This had profound effects on climate and ocean circulation. The interior of the massive continent became arid, while the coasts remained wet and tropical. This period also saw one of the most severe extinction events in Earth's history. The Permian-Triassic extinction, which occurred about 252 million years ago, wiped out over 90% of all species. The exact cause is still debated, but it likely involved massive volcanic eruptions in what is now Siberia, which released enormous amounts of greenhouse gases and toxic substances into the atmosphere. But life, as always, found a way to recover. The Triassic period that followed saw the rise of the dinosaurs, which would dominate Earth's terrestrial ecosystems for over 160 million years. This was also when the first mammals appeared, though they remained small and relatively insignificant while dinosaurs ruled the planet. The Mesozoic era, often called the Age of Reptiles, was a time of warm climates, high sea levels, and lush vegetation. Flowering plants evolved and diversified, creating the first recognizably modern ecosystems. The first birds evolved from small dinosaurs, mastering flight and opening up entirely new ecological niches. Around 66 million years ago, Earth faced another catastrophic extinction event. A massive asteroid, probably about 10 kilometers in diameter, struck the Yucatan Peninsula in Mexico. The impact released energy equivalent to billions of nuclear bombs, throwing massive amounts of debris into the atmosphere and blocking out the sun for months or even years. This impact, combined with other environmental changes, led to the extinction of non-avian dinosaurs and about 75% of all species on Earth. But it also created opportunities for the survivors. Small mammals, which had lived in the shadows of dinosaurs for over 100 million years, suddenly found themselves in a world with many vacant ecological niches. The Cenozoic era that followed saw the rapid diversification of mammals. Without dinosaurs to compete with, mammals evolved into an incredible variety of forms. Some became huge, like the woolly mammoth and giant ground sloths. Others took to the air, like bats, or returned to the sea, like whales and dolphins. The climate during the early Cenozoic was generally warm and tropical, but it gradually cooled over millions of years. Around 34 million years ago, Antarctica became covered in ice for the first time in hundreds of millions of years. The global cooling continued, leading eventually to the ice ages of the Quaternary period. The ice ages, which began about 2.6 million years ago, saw repeated advances and retreats of massive ice sheets across much of North America and Europe. These dramatic climate changes drove evolution and migration patterns, shaping the modern distribution of species around the world. It was during this time that our own species story began. The first human ancestors appeared in Africa around 7 million years ago. These early hominids were still very ape-like, but they had begun walking upright, a crucial adaptation that freed their hands for tool use. Over millions of years, human ancestors evolved larger brains, more sophisticated tools, and complex social behaviors. Around 300,000 years ago, modern humans, Homo sapiens, first appeared in Africa. For most of their existence, humans lived as hunter-gatherers in small groups, having relatively little impact on the global environment. But around 12,000 years ago, humans began developing agriculture, learning to cultivate plants and domesticate animals. This led to the first permanent settlements, then cities, then civilizations. The human population began growing exponentially, and human impact on the environment increased dramatically. The development of agriculture marked the beginning of the Anthropocene, the current geological era defined by human influence on Earth's systems. In just a few thousand years, a blink of an eye in geological terms, humans have transformed the planet's surface, altered its climate, and driven thousands of species to extinction. Today, Earth is home to an estimated 8.7 million species, from microscopic bacteria to massive blue whales. The planet's surface is 71% water and 29% land, with 7 continents separated by 5 oceans. The atmosphere is 78% nitrogen and 21% oxygen, with trace amounts of other gases including the carbon dioxide that is driving current climate change. The story of Earth is still being written. Our planet continues to change, driven by tectonic forces, climate cycles, and increasingly human activity. Continents are still moving, mountains are still rising and eroding, and new species are still evolving while others become extinct. Looking to the future, Earth will continue to evolve. In a few 100 million years, the continents may merge into a new supercontinent. In about 1 billion years, the sun will have grown so bright that Earth's oceans will boil away. And in about 5 billion years, the sun will expand into a red giant, likely engulfing Earth entirely. But for now, in this moment in cosmic time, Earth remains the only known planet that harbors life. It is a world of incredible beauty and complexity, from the deepest ocean trenches to the highest mountain peaks, from frozen polar ice caps to scorching tropical deserts. The story of Earth's formation and evolution is also our story. Every element in our bodies was forged in the heart of ancient stars: the calcium in our bones, the iron in our blood, the oxygen we breathe. All of it has a history stretching back billions of years to the birth of our planet and beyond. We are not separate from Earth's story. We are part of it. We are the latest chapter in a 4.6 billion-year epic of cosmic violence, patient transformation, and the endless creativity of natural processes. We are stardust that has learned to contemplate the stars, matter that has become conscious of itself, life that has begun to understand its own origins. As we face the challenges of the 21st century: climate change, biodiversity loss, resource depletion, it's worth remembering that our planet has survived far worse catastrophes. Earth has been a frozen snowball, a molten hellscape, and everything in between. Life has persisted through mass extinctions, asteroid impacts, and dramatic climate shifts. This doesn't mean we should be complacent about current environmental challenges. On the contrary, understanding Earth's history should inspire us to be better stewards of our planet. We are the first species in Earth's history with the power to consciously influence the planet's future. With that power comes responsibility. The story of Earth reminds us that our planet is both incredibly resilient and remarkably fragile. It has survived billions of years of cosmic accidents and catastrophes, but it has also undergone irreversible changes. The Earth of today is not the same as the Earth of a billion years ago, and the Earth of the future will be different again. What makes our moment in Earth's history unique is that for the first time, one species has the knowledge and power to consciously shape the planet's future. We can choose to be a force for destruction, like the asteroid that killed the dinosaurs, or we can choose to be a force for creation and preservation. The choice is ours, and the consequences will echo through geological time. Future generations, perhaps even future species, will look back on our era as a crucial turning point in Earth's story. What kind of chapter will we write in the ongoing epic of our beautiful, complex, ever-changing planet? This is the story of Earth, a story of incredible journeys through space and time, of catastrophic endings and miraculous beginnings, of the slow transformation of lifeless rock into a living world. It's a story that began 4.6 billion years ago in a cloud of cosmic dust, and it continues today in every breath we take, every step we make, and every choice we make about the future of our one and only home in the universe. From the first stirrings of gravity in a stellar nursery, to the emergence of conscious beings capable of contemplating their own existence, Earth's story is the most remarkable tale ever told. And the most remarkable part? It's still being written, and we all have a role to play in what comes next. But there are countless details and fascinating chapters in this epic story that deserve deeper exploration. Let us dive deeper into some of the most remarkable periods and events that shaped our world, for each era holds secrets and wonders that reveal just how extraordinary our planet's journey has been. The Hadean Eon, Earth's earliest period, lasted from about 4.6 to 4.0 billion years ago, and it was named after Hades, the ancient Greek underworld, because conditions were so hellish. During this time, Earth was constantly bombarded by asteroids and comets in what scientists call the Late Heavy Bombardment. These impacts were so frequent and violent that they kept the planet's surface molten for millions of years. The sky would have been filled with streaking meteors, and the ground would have glowed red-hot like the inside of a furnace. The atmosphere during the Hadean was nothing like today's. It was probably composed mainly of hydrogen and helium captured from the solar nebula, along with gases released by volcanic activity and impacts: water vapor, carbon dioxide, nitrogen, methane, ammonia, and hydrogen sulfide. The pressure was intense, perhaps 100 times greater than today's atmosphere. Lightning storms raged constantly through the thick, toxic air, and the temperature at the surface could reach 1,200 degrees Celsius. Yet, even in this apparent hell, the building blocks of life were being assembled. The constant bombardment brought water to Earth in the form of comets and asteroids. Volcanic activity released gases and minerals from the planet's interior. The intense energy from impacts, lightning, and ultraviolet radiation drove chemical reactions that created increasingly complex organic molecules. In the depths of the oceans near volcanic vents, where temperatures and chemical gradients created unique conditions, the first self-replicating molecules may have formed. The formation of the Moon through the giant impact had consequences that extended far beyond creating Earth's satellite. The collision stripped away much of Earth's original atmosphere, allowing a new one to form from volcanic outgassing. The debris that formed the Moon was initially much closer to Earth than it is today, creating massive tides that may have been hundreds of meters high. These extreme tidal forces helped mix the early oceans, and may have created the kind of rhythmic cyclical conditions that encouraged the formation of complex chemistry. The Moon's gravitational influence also slowed Earth's rotation. In the early days after the giant impact, an Earth day lasted only about 6 hours. Gradually, tidal friction transferred energy from Earth's rotation to the Moon's orbit, slowing our planet's spin and causing the Moon to recede. This process continues today, with the Moon moving about 3.8 centimeters farther from Earth each year, and Earth's day getting longer by about 1.7 milliseconds per century. As the late heavy bombardment finally subsided around 3.8 billion years ago, Earth began to settle into a more stable state. The crust solidified into the first continents. Though these were much smaller than today's landmasses, the early continents were made primarily of granite and other light-colored rocks that float on the denser mantle below. These proto-continents were constantly being reshaped by volcanic activity and the movement of tectonic plates. The early oceans were vastly different from today's seas. They were much hotter, with temperatures possibly reaching 70–85 degrees Celsius near the surface. The water was acidic and rich in dissolved minerals, including high concentrations of iron that would later play a crucial role in Earth's history. There was no oxygen in the water or atmosphere, so the oceans had a greenish tint from dissolved iron and other chemicals. Into this alien world came the first life forms, and their story is one of the most remarkable chapters in Earth's history. These early organisms, called extremophiles, because they thrived in conditions that would kill most modern life, were incredibly diverse in their chemical processes. Some fed on sulfur compounds near volcanic vents, others consumed methane, and still others derived energy from the breakdown of organic compounds that had formed through non-biological processes. One group of these early organisms, the methanogens, produced methane as a waste product. This methane accumulated in the atmosphere, creating a powerful greenhouse effect that helped keep Earth warm despite the sun being about 30% dimmer than it is today. This is known as the faint young sun paradox, how Earth remained warm enough for liquid water when the sun was so much cooler. The answer lies partly in these early life forms and their impact on atmospheric chemistry. The evolution of photosynthesis around 3.5 billion years ago was perhaps the most revolutionary development in the history of life. The first photosynthetic organisms were cyanobacteria, and they fundamentally changed the chemistry of Earth's atmosphere and oceans. Unlike the chemical processes that earlier life forms had relied on, Photosynthesis could harness the virtually unlimited energy of sunlight to convert carbon dioxide and water into organic compounds. But photosynthesis had a dramatic side effect. It produced oxygen as a waste product. For the anaerobic organisms that had dominated Earth for over 1 billion years, oxygen was deadly poison. The accumulation of oxygen in the atmosphere, which began around 2.4 billion years ago during the Great Oxidation event, caused the first mass extinction in Earth's history. It's estimated that up to 99% of all anaerobic life forms were wiped out. The Great Oxidation event didn't happen overnight. It took hundreds of millions of years for oxygen levels to rise significantly, and the process was not smooth or steady. There were periods when oxygen levels rose rapidly, followed by crashes as the gas was absorbed by chemical reactions with rocks and dissolved metals in the oceans. The most dramatic evidence of this process can be seen in banded iron formations, layers of iron-rich rock that formed when oxygen combined with dissolved iron in the oceans, causing it to precipitate out of solution. As oxygen levels rose, they triggered other dramatic changes in Earth's environment. The oxygen reacted with methane in the atmosphere, removing this powerful greenhouse gas and causing global temperatures to plummet. Around 2.4 billion years ago, Earth experienced its first major ice age, known as the Huronian glaciation. Ice sheets may have extended all the way to the equator, turning Earth into what scientists call a snowball Earth. The Huronian glaciation lasted for about 300 million years, but life found ways to survive even these extreme conditions. Some organisms evolved antifreeze proteins, others retreated to geothermal areas where volcanic heat kept water liquid, and still others entered states of dormancy that allowed them to wait out the harsh conditions. When the Ice Age finally ended, it set the stage for the next major evolutionary leap, the development of eukaryotic cells. These cells were fundamentally different from their prokaryotic predecessors. They had a membrane-bound nucleus containing their genetic material, and they possessed specialized internal structures called organelles that could perform specific functions. The evolution of eukaryotic cells involved one of the most remarkable partnerships in the history of life. According to the endosymbiotic theory, developed by biologist Lynn Margulies, eukaryotic cells formed when larger cells engulfed smaller ones, but instead of digesting them, the two began living together in a mutually beneficial relationship. The smaller cells became organelles like mitochondria, which produce energy for the cell, and chloroplasts, which perform photosynthesis in plant cells. This partnership was so successful that it became permanent. Today, every complex organism on Earth, from giant sequoia trees to blue whales to humans, is made up of eukaryotic cells that contain these ancient bacterial partners. In a very real sense, we are all walking ecosystems, carrying within ourselves the descendants of bacteria that first formed this partnership over 2 billion years ago. The development of sexual reproduction around the same time was another revolutionary change. Instead of simply copying themselves like bacteria do, eukaryotic organisms began exchanging genetic material with each other. This dramatically accelerated evolution by creating new combinations of genes and allowing beneficial mutations to spread more rapidly through populations. For the next billion years, Earth was dominated by single-celled eukaryotic organisms. This period, sometimes called the Boring Billion, was actually a time of crucial evolutionary development. Organisms were experimenting with different ways of living, developing more complex cellular processes, and gradually increasing in size and complexity. The late Proterozoic period, around 1.5 billion years ago, saw the first tentative experiments with multicellularity. Some organisms began forming colonies, where different cells performed different functions. This was the beginning of the division of labor that would eventually lead to complex organisms with specialized tissues and organs. Around 800 million years ago, Earth experienced another series of severe ice ages, known as the Cryogenian period. These were even more extreme than the earlier Huronian glaciation, with ice covering most or possibly all of the planet's surface. The Snowball Earth episodes lasted for millions of years at a time, and came close to extinguishing life entirely. But these extreme conditions may have actually spurred evolutionary innovation. The stress of surviving in such harsh environments favored organisms that could adapt quickly and work together. When the ice ages finally ended, they were followed by an explosion of evolutionary innovation that led to the first complex multicellular life forms. The Ediacaran period, from 635 to 541 million years ago, was named after the Ediacaran Hills in Australia, where the first fossils of these ancient organisms were discovered. The creatures of this period were unlike anything alive today. They were soft-bodied and often large, some reaching over a meter in length. They had strange geometric patterns and lived peacefully on the sea floor, with no predators to threaten them. Some Ediacaran organisms looked like quilted mattresses, others resembled ferns or discs, and still others had fractal patterns that repeated at different scales. They fed by absorbing nutrients directly through their skin, or by filtering them from the water. It was a Garden of Eden beneath the waves, a world without violence or competition. But this peaceful world was about to end. The Cambrian Explosion, which began 541 million years ago, introduced predation to the world's oceans and triggered an evolutionary arms race that continues to this day. In a relatively short span of geological time, organisms developed shells, claws, eyes, and sophisticated behaviors. The Cambrian seas were filled with some of the most bizarre creatures ever to live on Earth. Wiwaxia looked like a medieval helmet covered in spines and scales. Opabinia had 5 eyes and a proboscis with a claw at the end. Percaea may have been one of the first vertebrates, a simple creature with a primitive backbone that was the ancestor of all fish, amphibians, reptiles, birds, and mammals. The most successful Cambrian animals were the trilobites, which dominated the oceans for over 270 million years. These arthropods had compound eyes that could detect light, movement, and polarization. Some species had eyes with over 15,000 individual lenses, giving them incredibly detailed vision. They were the first organisms to develop sophisticated visual systems, and their success demonstrates the enormous evolutionary advantage that comes with being able to see the world clearly. The development of complex ecosystems during the Cambrian was driven by the evolution of predation. For the first time in Earth's history, organisms were actively hunting and eating each other. This created powerful selective pressures that favored innovations like hard shells for protection, better mobility for escape, and improved sensory systems for detecting threats and opportunities. The early Paleozoic era saw life begin its conquest of land, but this process was much more gradual and difficult than the Cambrian explosion in the oceans. Land presented unique challenges. There was no water to provide buoyancy and nutrients, no protection from ultraviolet radiation, and extreme temperature variations between day and night. The first colonizers of land were probably cyanobacteria and other simple organisms that could form thin films on rocks and soil. These pioneer species began the long process of breaking down rock into soil, creating conditions that would eventually support more complex life. Lichens, which are partnerships between fungi and algae, were among the most successful early land colonizers. The evolution of plants from aquatic algae required numerous innovations. Plants had to develop waxy coatings to prevent water loss, root systems to absorb water and nutrients from soil, and structural support systems to stand upright without the buoyancy of water. The first land plants were small and simple, staying close to water sources and reproducing through spores. Around 400 million years ago, plants developed seeds, which could survive long periods of drought and cold. This innovation allowed plants to spread into drier environments and gave rise to the first forests. Trees evolved multiple times independently, demonstrating the enormous advantage of height in competing for sunlight. The evolution of wood was another crucial innovation. Wood is primarily made of lignin, a complex polymer that provides structural support and allows trees to grow tall. The evolution of lignin-producing plants created the first forests and dramatically changed Earth's landscape and climate. These early forests were very different from modern ones. They were dominated by giant ferns, horsetails, and early seed plants. Some ferns grew to be 30 meters tall, creating cathedral-like forests with a canopy that blocked out most sunlight from reaching the ground. When these plants died, they often fell into swamps where the lack of oxygen prevented complete decay. Over millions of years, these partially decayed plants were compressed into coal, which is why this period is called the Carboniferous. The abundance of plant life during the Carboniferous had a dramatic impact on atmospheric chemistry. Plants removed enormous amounts of carbon dioxide from the atmosphere, storing it in their bodies and eventually in coal deposits. Oxygen levels rose to about 35% of the atmosphere, compared to 21% today. This oxygen-rich atmosphere had profound effects on life, allowing insects to grow to enormous sizes. Giant dragonflies with wingspans of 70 centimeters patrolled the Carboniferous skies. Millipedes over 2 meters long crawled through the forests. These giant arthropods were possible because of the high oxygen levels, which allowed their simple respiratory systems to supply oxygen to large bodies. The colonization of land by vertebrates began with the evolution of amphibians from fish around 365 million years ago. The transition from water to land required numerous adaptations: lungs for breathing air, legs for walking, changes in sensory systems to work in air rather than water. Early amphibians like Acanthostega and Ichthyostega were still very fish-like, with 8 toes and gills as well as lungs. The evolution of the amniotic egg around 340 million years ago was crucial for vertebrates' complete conquest of land. Unlike amphibian eggs, which must be laid in water, amniotic eggs have protective shells and internal fluid that creates a water environment for the developing embryo. This allowed reptiles to reproduce far from water sources and colonize dry inland areas. Early reptiles diversified rapidly into numerous ecological niches. Some became large herbivores that fed on the abundant plant life. Others became predators that hunted other reptiles and amphibians. The sail-backed Dimetrodon, often mistaken for a dinosaur, was actually more closely related to mammals and used its sail to regulate body temperature. The end of the Paleozoic era was marked by the most severe extinction event in Earth's history. The Permian-Triassic extinction, which occurred 252 million years ago, wiped out about 96% of marine species and 70% of terrestrial species. The exact cause is still debated, but it likely involved massive volcanic eruptions in what is now Siberia. These eruptions, known as the Siberian Traps, released enormous amounts of lava, ash, and toxic gases into the atmosphere. The volcanic activity may have continued for hundreds of thousands of years, drastically altering global climate and ocean chemistry. The oceans became acidic and lost much of their oxygen, creating dead zones where nothing could survive. But life, as always, found a way to recover. The Triassic period that followed saw the rise of the dinosaurs, which would dominate terrestrial ecosystems for the next 165 million years. The first dinosaurs were small, bipedal creatures that looked more like modern birds than the giant sauropods that would evolve later. The Mesozoic era, often called the Age of Reptiles, was characterized by warm, stable climates and high sea levels. There were no polar ice caps, and even Antarctica was covered by temperate forests. This greenhouse world supported an incredible diversity of life, including some of the largest land animals that ever lived. The evolution of flowering plants during the Cretaceous period created the first recognizably modern ecosystems. Flowers allowed plants to form partnerships with insects and other animals for pollination, leading to coevolution between plants and their pollinators. This created more complex and interconnected ecosystems than had existed before. The first grasses evolved during the Cretaceous, though they wouldn't become dominant until after the extinction of the dinosaurs. Grass is an incredibly successful plant form because it grows from the base rather than the tip, allowing it to survive being eaten by grazers. The evolution of grasslands would later support vast herds of mammals and shape the evolution of our own species. Marine ecosystems during the Mesozoic were dominated by reptiles rather than fish. Plesiosaurs, with their long necks and flippers, were the dominant marine predators. Ichthyosaurs evolved to look remarkably like modern dolphins, demonstrating convergent evolution. Mosasaurs, giant marine lizards, ruled the seas during the late Cretaceous. The asteroid impact that ended the Mesozoic was one of the most dramatic events in Earth's history. The asteroid, estimated to be about 10 pisti 15 kilometers in diameter, struck the Yucatan Peninsula with the force of billions of nuclear bombs. The impact created a crater over 150 kilometers wide and sent shockwaves around the planet. The immediate effects of the impact were catastrophic. A fireball of vaporized rock and gas expanded outward from the impact site, igniting fires across much of North America. Tsunamis, hundreds of meters high, swept across the oceans, but the long-term effects were even more devastating. The impact threw enormous amounts of debris into the atmosphere, blocking out sunlight for months or even years. This caused global temperatures to plummet and prevented photosynthesis, causing the collapse of food chains. Acid rain fell from the sky as sulfur compounds in the impactor and target rocks combined with water vapor in the atmosphere. The extinction that followed was selective in ways that reveal important principles about survival and evolution. Small animals were more likely to survive than large ones, probably because they required less food and could hide in burrows or other shelters. Animals that could eat seeds, nuts, and detritus survived better than those that relied on fresh vegetation. Animals with lower metabolic rates, like crocodiles and turtles, fared better than those with high metabolic rates, like dinosaurs. The survival of birds, which are dinosaurs, demonstrates that the extinction was not complete. Birds possessed several advantages. They were small, they could fly to find food and shelter, and many species ate seeds that could survive long periods of darkness and cold. The recovery from the mass extinction took millions of years, but it opened up tremendous opportunities for the survivors. Mammals, which had lived in the shadows of dinosaurs for over 100 million years, suddenly found themselves in a world full of empty ecological niches. The early Cenozoic saw an explosive radiation of mammalian forms. Within 10 million years of the extinction, mammals had evolved to fill many of the roles previously occupied by dinosaurs. Some became large herbivores, others became swift predators, and still others took to the trees or returned to the sea. The evolution of grass during the Cenozoic created new opportunities and challenges for mammals. Grasslands support different kinds of ecosystems than forests, favoring animals that can run fast across open terrain rather than climb through trees. This led to the evolution of horses, antelopes, and other fast-running mammals, as well as the predators that hunted them. The return of mammals to the sea produced some of the most remarkable evolutionary transformations in the fossil record. Whales evolved from small, four-legged mammals that lived near the shore and gradually became more and more aquatic. Early whales like Ambulocetus could walk on land and swim in water, while later forms like Basilosaurus were fully aquatic but still retained tiny hind legs. The evolution of echolocation in dolphins and toothed whales represents one of the most sophisticated sensory systems ever evolved. These animals can create detailed three-dimensional maps of their environment using sound waves, allowing them to hunt in complete darkness and navigate through murky water. The global cooling that began in the Middle Cenozoic was driven by several factors, including the formation of the Antarctic ice sheet. The collision of India with Asia created the Himalayan mountains, which altered global wind patterns and removed carbon dioxide from the atmosphere through weathering processes. Around 34 million years ago, Antarctica became isolated at the South Pole and began accumulating ice. This marked the beginning of the current icehouse climate state, with permanent ice at both poles. The formation of ice caps had profound effects on global climate and sea level, creating new environmental challenges and opportunities. The Quaternary ice ages, which began about 2.6 million years ago, saw repeated advances and retreats of massive ice sheets across much of the northern hemisphere. These glacial cycles were driven by variations in Earth's orbit around the Sun, known as Milankovitch cycles, but their effects were amplified by feedback mechanisms in Earth's climate system. During glacial periods, So much water was locked up in ice sheets that global sea levels were 120 meters lower than today. This exposed land bridges between continents and islands, allowing plants and animals to spread to new areas. The Bering Land Bridge connected Asia and North America, allowing humans and other mammals to migrate between the continents. The Ice Ages also created unique ecosystems that no longer exist today. The Mammoth Steppe was a cold, dry grassland that stretched across northern Europe, Asia, and North America. It supported vast herds of mammoth, woolly rhinoceros, bison, and horses, along with predators like cave lions and saber-toothed cats. It was during the Quaternary that our own species' story began in earnest. The earliest human ancestors appeared in Africa around 7 million years ago, but the evolution of our lineage was gradual and involved many different species. Early hominids like Australopithecus were still very ape-like, but had begun walking upright, a crucial adaptation that freed their hands for tool use. The evolution of larger brains in human ancestors was driven by multiple factors: the advantages of tool use, the complexity of social cooperation, the need to find and process difficult-to-obtain foods, and possibly the cognitive demands of language. Brain expansion came at a significant cost, as human brains consume about 20% of our body's energy, but the benefits clearly outweighed the costs. The development of stone tool technology around 2.6 million years ago marked a crucial turning point in human evolution. Tools allowed our ancestors to access new food sources, process materials more efficiently, and defend themselves against predators. The sophistication of stone tools increased gradually over millions of years, reflecting growing cognitive abilities and cultural transmission of knowledge. The control of fire, which occurred sometime between 400,000 and 1.5 million years ago, was perhaps the most important technological development in human history. Fire provided warmth, protection from predators, and the ability to cook food. Cooking made many foods more digestible and may have contributed to further brain evolution by making more nutrients available. Modern humans, Homo sapiens, first appeared in Africa around 300,000 years ago. For most of their existence, humans lived as hunter-gatherers in small, nomadic groups. They developed sophisticated tools, art, music, and oral traditions, but their impact on the environment was relatively limited. The migration of humans out of Africa and around the world was one of the most remarkable journeys in the history of life. Humans reached Australia by 50,000 years ago, Europe by 40,000 years ago, and the Americas by at least 15,000 years ago. Each new environment presented unique challenges and opportunities that shaped human culture and technology. The development of agriculture around 12,000 years ago marked the beginning of the modern world. Instead of simply harvesting what nature provided, humans began deliberately cultivating plants and domesticating animals. This allowed much larger populations to live in smaller areas and led to the first permanent settlements. Agriculture developed independently in several different regions around the world, suggesting that it was an almost inevitable development once humans had reached a certain level of cultural sophistication. The crops and animals domesticated in each region reflected local conditions: wheat, barley, and sheep in the Middle East, rice and pigs in China, corn, beans, and squash in the Americas, and various African crops like sorghum and yams in Africa. The agricultural revolution transformed not just human society but also the global environment. Forests were cleared for farmland, wetlands were drained, and new landscapes were created to serve human needs. The populations of wild animals declined as their habitats were converted to agricultural use, while the populations of domestic animals increased dramatically. The rise of cities and civilizations followed the development of agriculture. With reliable food supplies, some people could specialize in activities other than food production: crafts, trade, governance, religion, and eventually science and art. The first cities appeared around 5,500 years ago in Mesopotamia. The invention of writing allowed humans to record and transmit knowledge across generations more effectively than ever before. This accelerated cultural evolution and led to the accumulation of increasingly sophisticated knowledge about the world. Mathematics, Astronomy, medicine, and engineering developed as humans sought to understand and control their environment. The Industrial Revolution, which began in the 18th century, marked another major turning point in Earth's history. For the first time, humans began using fossil fuels on a large scale, releasing carbon that had been stored underground for hundreds of millions of years. This initiated the current period of rapid climate change and marked the beginning of what many scientists call the Anthropocene. Today, human activities affect virtually every aspect of Earth's systems. We have altered the composition of the atmosphere, changed the chemistry of the oceans, modified the flow of rivers, and transformed landscapes on every continent. We have driven many species to extinction while spreading others far beyond their natural ranges. Yet this same species that has caused so much environmental change also possesses unprecedented knowledge about Earth's history and systems. We understand the mechanisms of climate change, evolution, and ecological interaction better than any species before us. We have the technological capability to modify our impact on the environment and potentially to prevent or mitigate the worst effects of our activities. The story of Earth is far from over. Our planet will continue to evolve, driven by geological processes, astronomical cycles, and increasingly conscious choices by the species that has learned to contemplate its own origins and influence its own future.